Hello everyone, I am Dr. Pranita Badve, Assistant Professor in Civil Engineering Department of MVP Samajas KBT College of Engineering, Nashik. In previous sessions, we have studied some properties of the fluid, its application into the field and its unit system. Now, in today's sessions, we are studying the remaining properties of the fluids in detail. Surface tension. It is defined as tensile force acting on the surface of the liquid in contact with gas or the surface between the two immiscible liquids, such that contact surface behaves like a membrane under the tension. Now here the two immiscible liquids means, let us take the example of the air and water. These are the two fluids which are not get mixed with each other. And if in between such a liquids, if any body is in contact, then the liquid surface behaves like a membrane under the tension, and therefore here in such a case surface tension is acting on the body. Now here surface tension is nothing but the tensile force acting over the unit length area. That means whatever the contact surface is there, over that contact surface, when such a body comes in contact, then tensile force is acting on such a liquid surface, and therefore tensile force per unit length can be defined as the surface tension. In Greek letter, the surface tension can be represented from the Greek letter sigma, and in unit system, the surface tension is measured in Newton per meter. These pictures are some practical applications of the surface tension. If any insect is on the surface of the liquid, then when it pulls its leg from the liquid surface, then up to some distance his leg is not lifted. It requires some force to lift that leg. This is because it takes the tensile force is acting over that length, and therefore this is the best example of the surface tension. Another example, if you drop any pin into the liquid surface, and if you want to take out that pin from the liquid surface, up to some distance, when you pull that pin from this liquid surface, up to some distance that water gets stretched. This is because of when you are applying the pulling force to that liquid surface, then that force is acting over that area, over that length, and this is nothing but the example for the surface tension. Let us derive the expression for surface tension on the liquid droplet. Now here we have considered the water droplet, in which that entire surface of the droplet is in contact with the air, and therefore the surface tension is acting on that surface of the water droplet. Let us consider sigma is the surface tension on the liquid, small p is the pressure intensity inside the droplet, and small d is the diameter of the droplet. Now here we have cut this water droplet into the two halves. The first force is acting as a tensile force due to the surface tension. Now this tensile force we can determine from the relation surface tension into the length. Now here the length of the droplet is nothing but the circumference of the droplet, and therefore the tensile force can be determined sigma into pi into d. Pi d is nothing but the circumference of this water droplet. Second force acting on the water droplet is the pressure force. This pressure force is acting towards the inner side of the half portion of the water droplet, and it is given from the relation pressure intensity into cross-sectional area of the water droplet. If we consider these two forces, pressure force is acting towards the inner side, and tensile force is due to the surface tension is acting in the outer side. So both the forces are having the same magnitude, but they are acting in the opposite direction. So therefore equating these two forces to determine the relation between the surface tension and the intensity of the pressure, and therefore here we have equated these two forces. Intensity of the pressure can be determined from the relation 4 sigma upon d. From this relation we can also determine the relation expression for the surface tension, which is equals to Pd upon 4. Second expression, surface tension on the hollow bubbles. Now in case of the hollow bubble, liquid membrane is in contact with the air from inner side as well as from the outer side. As this liquid membrane is in contact with the air from inner side and outer side, so therefore here two surfaces are subjected to the surface tension. So like your previous case, here we are multiplying it by the 2 for determining the tensile force on the liquid membrane. After equating these two forces, we are obtaining the expression for the intensity of the pressure 8 sigma upon D. Or from this relation, we can also determine the expression for the surface tension, which is equals to PD upon 8. Third expression is surface tension on the liquid jet. Now here consider this liquid jet of diameter D and length capital L. Now here if we cut that liquid jet into the two halves, then at the outer side the surface tension is acting, that is the tensile force is acting. Towards the inner surface of that jet, that pressure force is acting. So therefore here we are considering the surface contact as well as the cross-sectional area of the liquid jet to determine the pressure force as well as to determine the tensile force. First, the force due to pressure. Here we are multiplying the area of the semi-jet to the intensity of the pressure. So area of the semi-jet will be the diameter of the jet and the length. So L into D is the area of the semi-jet multiplied by the P. Next force is due to the surface tension. Here the sigma is multiplied by the 2L. Now these two forces we are equating to determine the relation between the intensity of the pressure, which is equals to 2 sigma upon D. Now from this relation we can also determine the relation between the sigma. Sigma is equals to PD upon 2. Next property of the fluid is the capillarity phenomena. What is basically capillarity phenomena? Let us consider container with a liquid, and into that if you pour the glass tube into that, then there might be the rise or fall of a liquid level in with the surrounding liquid level. This rise or fall of a liquid level inside the small tube is nothing but the capillarity phenomena. So if there is a rise of liquid level into that small tube, then it is called as the capillary rise, and if there is a reduce or what we can say is the fall of liquid level into that tube, then it is called as the depression. So rise or fall of a liquid level into the tube is called as the capillarity. What is its units? Capillarity phenomenon can be measured in terms of centimeter or in terms of mm of liquid. The value of capillarity depends upon some factors. So very first factor is the specific weight of the liquid, second one is the diameter of the tube, and third one is nothing but the surface tension of the liquid. First, let us take the example of the water and mercury. If you pour the tube into that water, due to its specific weight, that water level rises into the tube. In other case, if we are considering the mercury, then if you pour the tube into that mercury, as the specific weight of the mercury is high than the water, so therefore there is a capillary depression into the tube. Second parameter is the diameter of the tube. If the diameter of the tube is very large, so you cannot observe the capillarity phenomenon into that. So instead, what we have to consider the tube such that its diameter should be less than 6 mm, so that we can observe the capillarity phenomenon into that tube. And third one is nothing but the surface tension. Surface tension of the liquid is also affecting to the value of the capillarity. These are some examples of the capillarity phenomenon that you can observe into the nature. The roots of the plants are taking the water with the capillary action. Secondly, the stems of the flowers are taking the water with their capillary action, similar to this lamp. Next is the expression for the capillary rise. Here in the container some liquid is there, and in between that small diameter tube is inserted. That tube is open from both the ends. Let small d is the diameter of the tube. The liquid level will rise into the tube above the level of the liquid. Let small h is the height of liquid into the tube. Now under the state of equilibrium, the weight of the liquid of height h is balanced by the force at the surface of liquid in the tube. But force at the surface of the liquid in the tube is due to the surface tension. Now sigma is the surface tension of the liquid. Let theta is the angle made by the vertical surface of the tube with the surface tension. So therefore the weight of the liquid of height h in the tube is given by volume into the rho g. Rho g is the weight density and volume is nothing but the area of the tube multiplied by h. So area of the tube we can get it from pi by 4 into d square into h into rho into g, where rho is nothing but the density of the liquid. Now the vertical component of the surface tensile force is given by sigma into circumference. Circumference is nothing but the pi into d and its vertical component. So it will be the sigma pi d into cos of theta. For the state of equilibrium condition, we are equating the weight of the liquid in the tube for height h with the surface tensile force in the upward direction. So after equating this, we are obtaining the value of h as 4 sigma cos of theta upon rho g into d. Here h is nothing but the rise of liquid level into the tube. Theta is the between the water and clean glass tube is approximately 0. The value of cos 0 is 1. So therefore the rise of liquid level in the tube h is given by the expression 4 sigma upon rho g d. Similarly, we can derive the expression for capillary fall. In the diagram, you can see that let us consider the mercury. If you are pouring the tube into that mercury, due to its specific weight, that mercury gets fall with the surrounding mercury level into the tank. So therefore, how much is the fall? That fall we can determine from this small h. Here, similar to the rise of liquid level into the tube, here the same forces are acting. First force due to the surface tension acting in the downward direction, which is determining from the formula sigma pi d into cos of theta, and second force, that is the hydrostatic force acting in the upward direction, which is getting from the relation intensity of the pressure into cross section area of the tube. So here pressure intensity we can determine from the hydrostatic law, that is the rho g into h, and here the total hydrostatic force acting in the upward direction is rho g h into pi by 4 d square. Now for the equilibrium, state of the equilibrium, we are equating both the forces as they are having the same value but they are in the opposite direction. So we are equating with each other. So from that relation we are obtaining the expression for h as 4 sigma cos of theta upon rho g d. Now in case of the mercury, the angle of theta, the value of angle of theta for mercury and glass tube is 128. So therefore that theta value is considered as a standard for the mercury. Next property of the liquid is the vapor pressure. The change of states from liquid to the gaseous is nothing but the process of vaporization. Let's see this diagram. In the diagram, in the one container, the liquid is there. And this container is covered with the lid. If you have given the heat from the bottom side, then liquid changes its states into the gases. These vapors are exerting the pressure on that liquid, and this phenomenon is nothing but the vapor pressure. See the definition of the vapor pressure. The accumulated vapors exerts a pressure on the liquid surface. This pressure is known as the vapor pressure of the liquid. Last property of the fluid is the cavitation. In the flowing liquid, if pressure at any point in the flowing liquid becomes equal to or less than the vapor pressure, then vaporization of the liquid starts. The bubble of these vapors are carried by the flowing liquid into the region of high pressure, where they collapse, giving rise to the high impact pressure. The pressure developed by the collapsing bubbles is so high that materials from the adjoining boundaries get eroded and cavities are formed. This phenomenon is called as the cavitation phenomenon.